Very good. So, good afternoon, everyone, and welcome to Recitation 2. So, today, first, I'm going to go through the problem 2.24 because it was in this week's homework, and a lot of people reached out to me in my office hours. So, I thought let's just go through it. And after that, I'm going to move forward with chapter 3 problems, which is going to be relevant for your next homework. So, let's just start. So in this problem, there is given a link which is attached to a mass and spring at one end, and in the lower end, it's attached to another spring with stiffness K2. And this is the equilibrium position. So we need to find the effective mass for the lower end N and also the natural frequency of the system. So first, I'm going to draw the free body diagram. So let's assume let X and Xn be the displacements of the two ends of link. So our diagram would look like this is the rod, and this is the pivot point. So in this end, it is attached to mass M. And the spring is K. And at this point, attached to spring with stiffness K2. So this was our equilibrium position. So I'll just say this displacement is X and this displacement is Xn. Also, we're given that this distance is B and this is A, and we're going to say this angle as theta. All right. So now from the triangle, we can see that X can be said as X equals to B sine theta. Similarly, Xn can be written as A sine theta. Since theta is small, we can assume that sine theta is equivalent to theta. So we can write X is equals to B theta and Xn is equals to A theta, which means theta can be written as X by B and as well as Xn by A. So if we equate those, we get X by B equals to Xn by A. So X would be equal to B by A, Xn. Question 1. Now, as you can see in this system, there is going to be two types of motion. One is the translation of the motion M, and another is going to be the rotation of the link, of this link. So next I'm going to find the equation of motion for both translation and rotation. So, and I'm going to draw a free body diagram from that. So let's just say this is for translational equation of motion for mass M. So our free body diagram would be, this is the mass M. We will have a spring force Kx, and let's just assume F as our reaction force, and also the displacement is in this direction. So now if I want to write the equation of motion and I'm taking this direction as positive, so I can write m double dot x equal to minus f minus kx. So f will be equivalent to minus mx dot minus kx. This is our equation 2. Now next I'm going to write the rotational equation of motion. Or link. So our free body diagram would be, this is the link, this is the pivot. So there would be a reaction force at this end, which is going to be F, and there is going to be a spring force, which will be K2xn. And this distance is B, this is A, and I'm going to call this is theta. Now, we know that the rotational equation of motion is J theta double dot equals to summation of M. For this case, I'm going to take it as point, this pivot point, I'm just calling it O, where J is the moment of inertia of linkage. So we can write J theta double dot. So I'm taking the counterclockwise as positive. So for the force F, then write F, the distance is B, and another force is K2xn, that would be clockwise, so it would be minus K2xn, and in this case the distance is A. And now from equation 2, here I'm just going to put the value of F, which is minus mx double dot minus kx multiplied by b minus a k2xn. Now I'm just going to simplify it. So it will be j theta double dot minus bmx double dot minus bkx minus ak2xn. Next, we're going to express the whole equation of motion is in terms of xn. So, expressing the equation of motion in xn. So we're going to use the following terms. One is theta naught is going to be, so theta naught is going to be x double dot n by a. As you remember, like xn was equal to a theta. We're also going to use x double dot is equal to b by a xn double dot, and x is obviously b by a multiplied by x. So now I'm just going to put all these values in this equation, and it will be j. So theta double dot equal to x naught double dot by a minus bm. It would be, so I'm putting the values of x double dot. It would be b by a x double dot n minus bk. I'm putting the value of x, which is b by a xn, and we have minus ak2 xn. Now our ultimate goal is to put this whole equation in the form of the standard equation of motion, which is m effective x double dot n plus j effective xn equals to 0. So now we are just going to simplify everything so that we can put into this standard form, and from that we will just equate it, the term before x double dot n as m effective mass, and the term before xn as the effective stiffness. So let's just do that. So I'm going to simplify it. J x double dot n by a here minus b square m x double dot n minus b square k xn minus a square k2 xn. So let the a will be cancelled out, and let's cancel out the a, and I'm just going to divide it with a square from here. So it will take a form like j by a square x double dot n minus b square by a square m x double dot n minus b square by e square k x n minus the a square get cancelled, minus k2 xn. So now if I group together everything before the x double dot n, I will get j divided by a square plus b square a square multiplied by n x double dot n. And now I'm going to group together everything before the xn. So it will be b square by a square k plus k2 xn equal to 0. So Now this is going to be our effective mass, and this is our effective stiffness. So let's just say M effective is equal to J by A square plus B square A square multiplied by M, and K effective is basically B square by A square K plus K2. Now, if we want to find the natural frequency, we know omega is equal to root over K effective plus M effective. So it's you're just going to put the value, and I'm not going to do the calculation anymore. So do any of you have any question about this problem? Hi. So we are going to do chapter 3 from next. So this is the only one problem I did from chapter 2. Okay, so now I'm going to move forward with the second problem. So this is 3.5. I think this is going to be covered in your homework. So in this problem, it's given that a spring mass system is excited by a force of F naught sine omega t, and when it is at resonance, so at resonance we know R is equals to 1. The x1 is given as 0.58, and at 0.80 resonance frequency, so let's just say R2 is equal to 0.8. The amplitude x2 is 0.46. Now we have to find the zeta of the system. So we know x is equals to f naught by k multiplied by 1 minus r squared plus 2 zeta r whole square. So for when r1 is r is equal to 1, so when r is equal to 1, we can write x1 is equals to f naught by k 1. It would be like 1 minus 1 whole square plus 2 zeta square, which will be ultimately x1 equals to f naught by k 2 zeta. We can write f naught by k is equals to x1 into 2 zeta, which is 0.58 into 2 zeta. Equation 1. Now, when r is equal to 0.8, we will write x2 is equal to f naught by k root over 1 minus r2 square whole square plus 2 zeta r2 whole square, or we can write it as x2 f naught k is equal to 2 zeta multiplied by 0.58 root over 1 minus R2 whole square plus Q zeta R2 whole square. Now we have to solve this equation to find the value of zeta. So x2 is equal to 0.46. I'm just taking this term in the side. So it would be like root over 1 minus R2 square whole square plus 2 zeta R2 whole square equals to 2 zeta multiplied by 0.58. So now I'm going to just square in both sides. So it would be 0.46 whole square multiplied by 1 minus R2 is 0.8 plus 2 zeta R2 square, and in this side we'll have 4 zeta multiplied by 0.5 square. So if we do the calculation, it will be 0.2116, and if I simplify it, this term will be equivalent to 0.1296 plus, and this would be 2.56 zeta square, and this is 1.3456 zeta square. So if I take everything with zeta square in one side, I'll get 0.8059 zeta square equals to 0.02782. So the result would be 0.1847. So does any of you have any question about this problem? Okay, so I'm going to move forward to the next problem. It's 3.15. So in this problem, it's given that there is a balanced wheel which is supported on spring, and it's rotating at a frequency of 1200 RPM. And it's given that the bolt is weighing 15 gram and the eccentricity is 5 centimeter. So we need to find out the buildup of vibration, which is basically the amplitude. If the system, if the natural frequency of the system is 18 cycle per second with a damping ratio of 0.10. So just to simplify, I'm going to draw the diagram. This is the spring. Okay. This is going to be the displacement, and omega is this direction, and this is ME. So you can write ME. M is 15 grams, so I'm just converting into kg, 0.015, and E is 5 centimeter. So 0.05, and the unit would be kg meter. We are given that W is 1200 RPM. So I'm going to convert it to radian per second. It's going to be 125.6 radian per second. Also, omega n is given as 18 cycle per second. So to convert it to radian per second, I'm going to multiply it with 2 pi. So we'll get 113.1 radian per second. Also, we are given zeta is equal to 0.1. And from this information, we can calculate R, which is omega by omega n. And to be 125.6 divided by 113.1, so R is equal to 1.1. So we know amplitude X is equal to F naught by K 1 root over 1 minus R square whole square plus 2 zeta R square. Now, F naught is equal to ME omega square. So we can write X is equal to ME omega square. We have a K here into multiplied by 1 minus R square whole square plus 2 zeta R whole square. Now, we can write that omega squared K is equal to R square by M. Now, I'm going to derive how it came. So here you can see omega by omega n is equals to R. Omega by omega n is equals to R. So omega square is equal to R square omega n square. So omega square can be written as R square by K by N. So that's how we got omega square by K is equals to R square by M. So let's just put it here, and our equation will become X equal to ME R square by M multiplied by root over 1 minus R square whole square plus 2 zeta R square. Now, if I put all the values, for ME, we have 0.015 multiplied by 0.05. R square is 1.1 whole square. The value of M is not given, so I'll just keep it as M. And in the it will be 1 minus 1.1 whole square, 1.1 square whole square plus 2 zeta is 0.1 to 1.1 whole square. And our final answer would be X equals to 0.00298 by M meter. Or you can also express that as 0.00, if we assume like m is equal to 1, 298 meter per kg. So do any of have any question about this problem? Okay, so I'll move to the next. So in problem 3.21, we're given that the spring of an automobile trailer is compressed as 10.16 centimeter, and and the wavelength is given as 14.63. We need to find the critical speed and also the amplitude of the vibration. So here, the compression, I'm going to express it as delta. So delta is equal to 0.1016 meter, and so from that we can find the frequency, and I will write this as Fm 1 by twice pi root over G by delta, and that would be 1 by 2 pi root over 9.81, 0.1016. And so the frequency would be 1.56 hertz. From that, we can find the omega. So omega n is equals to 2 pi fn. So it would be 2 pi 1.56, and so the omega will be equivalent to 9.84 radian per second. Now, sorry. So the V is given at 64.4 kilometer per hour. So I'm just going to convert it as meter per second. V is equal to 64.4 kilometer per hour. So in the meter per second, it would be 17.89 meter per second. So we know F is equal to, we can also write it as F is equal to V by wavelength. Here, this is wavelength. So F is 17.89 divided by the wavelength is given as 14.63. So F would be equivalent to 1.22. From that, we can find omega, which would be 2 pi f 2 pi at 1.32. So our omega is 7.683 radian per second. So once we got this, we can find our R, which is omega by omega n, and that will be 7.683 divided by 9.824. Now next, since we're going to use the R square in the equation, I'm just directly putting the value of this 17.68 9.824 whole square is equal to 0.6117. Also, we were given the force Y was equal to, let's just say, A sine omega t, where the value of A is given as, amplitude 7.62 centimeter. So it's 7.62 into sine, and we just find the value of omega as 7.683 t. Our goal is to find the amplitude which is x by y naught, or y naught equals to root over 1 plus 2 zeta r whole square divided by 1 minus r square whole square plus 2 zeta r whole square. So since we're going to find it at let me just check. So we're going to, so it said that it's going to be the critical speed and we have to neglect the damping. So zeta will assume zeta as 0 here. So then it will become x divided by y naught 1 plus 1 minus r squared. So x is going to y naught 1 minus r squared. Y naught was this 7.62. minus, and we found r square as 0.6117. So the value of x would be 19.64 centimeter. So let me know if you have any question about 3.21. Okay, good. So I'm going to move to the next problem. So So this is going to be our last problem for today. So in this problem, it's given there is an industrial machine which has a mass of 453.4 kg, and it's supported on spring with a deflection of 0.508 centimeter. And the machine has a rotating unbalance of 0.23 kg. So first we have to determine the force transmitted to the floor at 1200 RPM, and then the dynamic amplitude at the speed. Also, it is said the assumed damping to be negligible, so we will assume that zeta is equal to 0. So first I'm going to write what is given in the problem. So the capital M, the mass of the machine, is 453.4 kg. And the static deflection, del, is equal to 0.508 into 10 to the power minus 2 meter. Also, we are given a rotating unbalance ME is equal to 0.2303 kg meter, and omega is given as 1200 RPM. If I express it in radian per second, it would be 125.6 radian per second. Now, we know that K delta, where delta is the deflection, is equal to mg. So you can write K is equal to mg by delta. So our mg is 453.4 G 9.81, and the deflection was 0.508 into 10 to the power minus 2. So from that we get our spring stiffness as 877561.8 Newton per meter. Since we have our K and M, we can find our omega n, the natural frequency. So we write over K by capital N. So K is this, and M is 453.4. So our omega is 43.94 radian per second. Now for part A, we need to find the transmitted force, which is called Ft. So we know Ft by F naught is equal to 1 plus 2 zeta r whole square, 1 minus r square whole square plus 2 zeta r whole square. Since the problem tells us to neglect the damping, so I'll set it zeta as 0. So then the equation will become ft by f naught equals to 1 into 1 divided by 1 minus r square. So ft would be f naught 1 minus r square modulus of ft. We can also write f naught is equals to m e omega square 1 minus r square. So if I just enter all the values, it would be 0.2303 multiplied by 125.6 whole square 1 minus r square is 0.1796. So we're going to take the modulus here. It would be 506.3 Newton. This is our transmitted force. For part B, we need to find the dynamic amplitude, which is x. X is equal to f naught by k multiplied by 1 divided by 1 minus r square whole square plus 2 zeta r whole square. So we're going to set zeta as 0. So our equation would be f naught is equal to m e omega square k multiplied by 1 minus r square. So if I put the values, it would be ME was ME was 0.23, omega square was 125.6, K was 875.61.8, and 1 minus r square is 8.1796. So if I calculate, the answer would be 0.006 meter. So do you have any question about problem 3.26? Okay, so I'll assume that we're good on that. So I'm going to post the videos